Okay, so we're going to continue with Unit 7, Worksheet 3, Circular Motion Examples. We're going to continue with problem number 2, which is where we left off. Previously, we talked about this problem, how we could set up both part A and part B. But now I'm going to go through solving the entirety of the problem rather than just the setup. So, just a refresher, for problem 2, we have 6 children running on a track with equal speeds. Their masses are expressed in terms of multiples of mass m, and their path radii are expressed in multiples of radius r. For part A, we are ranking the centripetal acceleration of the lettered children from the largest to the smallest, keeping in mind that ties are possible. Now, what I have up here in the blue font is going to be the equation for our centripetal acceleration. It is our tangential velocity, or the speed, squared, divided by the radius. And then to the right of that, that's where we solved for the centripetal acceleration for A. Because they have a radius of 4r, that's why I put that on the denominator. We weren't told anything about their tangential velocity, so we just left that as v squared. We rearranged it knowing that all of these are going to have the same tangential velocity, so the v squared is going to be constant for every single runner, and they're always going to have some multiple of r. So that's why we have the v squared divided by r by itself. The prefix is what we're focusing on. For runner A, because they have a path radii of 4r, we pulled out that r, and then they also have a prefix of 1/4. This is also going to be true of D. For D, they also have 1/4 tangential velocity squared divided by the radius, because they are on the same path length. For runners B and E, these are both on the 5r path. So both of these are going to have that prefix of 1/5. And then they still have the tangential velocity squared divided by the radius. And then C and F are both going to be on the 6r path. So for C and F, they are going to have that prefix of 1/6 tangential velocity squared divided by the radius. So at this point, we're just going to be focusing on the prefixes. A and D both have the same prefix, 1/4, which if we were to represent that as a decimal is 0.25. For B and E, they both have the same prefix of 1/5. As a decimal, that's 0.2. And C and F also have that same prefix, and as a decimal, that would be 0.167, which I'm just going to round to 0.17. It's easier to compare these two in decimal form rather than the fractional form, because we'd have to rearrange it to all have the same denominator. So I'm just going to represent these in terms of decimals. So we can see that A and D both have the largest centripetal acceleration. A and D. I'm saying those two are equal to each other. Both of these are going to be greater than our next one, which is going to be B and E. And these two are equal to each other. Both of those are going to be equal than C and F, which are also equal to each other. So that's how we can represent the centripetal acceleration. Now for part B, we're ranking the centripetal force needed for each child to remain in circular motion. What I have down here on the bottom left is the equation for our centripetal force, or the net force acting on an object. It's mass times our centripetal acceleration, or mass times our tangential velocity squared divided by the radius. And then on the bottom right is where I have our setup for part A. Because they have a mass of 4m and a radius of 4r, I pulled out those numbers, the 4 on the numerator and the 4 on the denominator, into the front, keeping in mind that what I've circled in red is going to be constant for every runner. The mass times the velocity squared divided by the radius. At this point, we're just going to be comparing the ratio between the mass and the radius to determine who has the biggest centripetal force needed to remain in circular motion. So A, we already saw, was going to be 1/1, or just 1. B is going to be 1 mass divided by 5 radius, or 0.2. C is going to be 6 mass over 6 radius, or 1. D is going to be 2 mass over 4 radius, or 0.5. E is going to be 3 mass over 5 radius, or 0.6. And finally, F is going to be 2 mass over 6 radius, or 0.3. Now, when we see it this way, we can end up actually having our ranking. The largest ratio we see is a 1-to-1 ratio, which both A and C have. So A is equal to C. The next biggest one we see is E. So A and C are both greater than E, which of 0.6. 0.6 is greater than D, which is 0.5, which is in turn is greater than F with our 0.3. And finally, B of 0.2 is going to be our last one. Oh, how'd that go purple? And sorry about the color change there. I must have tapped the purple instead of the green. But anyway, this is how we're going to solve all of problem 2, part A, and part B.